Hello, I'm Wojciech Janczewski, and I will talk about my joint work with Paweł Gawrychowski on algorithm for dynamic approximated longest increasing subsequence working in polylogarithmic time. So the problem of finding the length of longest increasing subsequence, in short LIS, is quite simple but fundamental problem in algorithmics, in which we are given an array of numbers and want to compute, well, the length of the longest increasing subsequence in that array. And here, please note that elements of this subsequence do not need to be consecutive in the array. Okay, and I will say that we want to compute length of LIS, although almost always solutions computing this length are also able to return increasing subsequence achieving this maximum length. So that's not a problem. Okay, and there exists a quite simple dynamic programming algorithm for LIS working in n log n time. And it is also known for a long time that in comparison model, this complexity of n log n is optimal. Although if we were to operate in word RAM model, and if numbers in an array are not too big integers, then by using some efficient predecessor structure, we could achieve n times log n complexity. So that's about it in the static case. So optimal complexities here are quite well understood, and problem itself is not that complex. So, but what about the dynamic variant, in which we want to be able to perform updates in our array? So by updates, I mean insertions or deletions of elements anywhere in the array. And after each such update, we should be able to report the length of LIS, current length of LIS, right? So the good news here is that it is easy to see that after a single update, length of LIS can change by at most 1, because inserting or deleting a single element cannot change increasing subsequence dramatically, right? But the bad news is that to report that length of LIS is some value, we probably would like to have stored in the background some subsequence, some increasing subsequence achieving this length, right? And unfortunately, maintaining some fixed increasing subsequence of maximum length seems to be problematic. So here's a simple example. Let's say that we have an array of numbers as presented, and there are a couple of different LISs there. So let's say that we fix our favorite one. It is of length 7. And then it can be the case that after a single update, here it's insertion of element 5 in the middle of the array, length of LIS increases by 1 from 7 to 8, but there is no simple way to update our previous fixed LIS to new LIS. We need to exchange quite lengthy part from the middle of it to some other elements of the array, right? So the bad thing here is that even though the length of LIS can change by at most 1, still, if we fix some LIS, then after even a single update, we might need to change its part of arbitrary length to have the new LIS, current LIS. Okay, so maybe first let's see what we can do already in this dynamic model. So sadly, extending the static solution doesn't give us too much. So it is possible to use it to handle updates on one of the ends of the array. So if updates happens only at the beginning or only at the end of the array, then we can handle them in logarithmic time. But even if we allow for updates on both sides on the array and not in the middle of this array, then already extending static approach seems to be hard. We don't know what to do this really, how to do this. So another thing we could try is parameterizing our complexity by length of LIS. So, and it has been done. So let's say that length of current LIS in the array is L. Then there exists a solution which can perform updates in time L times logarithm from N over L. Okay, so that can be nice, but still L, length of LIS, can be linear in N. So in worst case, it's not much better than just running Friedman's algorithm from the scratch after every update. Okay, so as solving this problem seems really hard, then we might try relaxing it and settle for computing just approximation of the current LIS, not the exact value, okay? And here by alpha approximation of LIS of length L, I mean just a number from range from L over alpha up to L over alpha up to L. Okay, and work on this approximation variant was started by Mitzenmacher and Sedigin recently. And they designed 1 over epsilon to the power of 1 over epsilon approximation of LIS, working in time n to the epsilon. Okay, so this might seem a bit lengthy, but what it essentially is just a constant approximation in arbitrarily small polynomial time, right? Although this constant in the approximation can be quite huge if you want to have a small running time. Okay, so this is pretty nice result because we can get we see that by using approximation we can get very efficient updates, not much faster than linear in time. But still, two questions were open. So first is, can we get down to polylogarithmic time? And second, can we get 1 plus epsilon approximation? And answers are positive. In our paper, we designed a 1 plus epsilon approximation of LIS, performing updates in still not too practical time, but nevertheless polylogarithmic time of log to 11th over epsilon to 5th. Okay. And so to do this, we need to actually consider more general queries. Let's call them extended LIS queries. And by that, I mean that we need to be able not only to report length of global LIS in the whole array, but we can also be queried about length of LIS in any subarray. So we can be given two indices, I and j, and we need to quickly answer what is the length of LIS in subarray starting at element I and ending at element j. Okay, and this is a generalization of our problem, but it's probably not asking for too much because, again, for the static case, there is an efficient solution for those extended LIS queries. Namely, there exists a structure of size just n log n, which can answer those queries in logarithmic time using Monge matrices. But this static solution seems to be quite hard to extend to the dynamic case, so we actually use a different approach. Namely, we use approximate covers and divide and conquer. Okay, so what would be one of the standard approaches to computing approximation of LIS? Well, let's say that we are able to check whether in a given interval, in a given subarray, exists increasing subsequence of size 1 plus epsilon to the power of k. Then if we are able to do this for all reasonable powers key, then by maintaining log n over epsilon levels of the structure for all reasonable values of key, we easily can get a good enough approximation, right? Because when we are asked about some interval, maybe we have no idea what exact value of LIS is, but for example, using binary search, we can get good enough approximation. Okay, but here the problem is again that to know that length of LIS is say 1 plus epsilon to k, we probably need to keep a witness of this value somewhere in the background. So increasing subsequence achieving this length. And the problem is if a single element of an array occurs in too many witnesses, then inserting such an element or deleting it can affect way too many places in our structure. Okay, and if we want to get polylogarithmic time, then we need to somehow deal with this problem. Okay, so let me introduce some simple definitions. So by a segment, I mean just a subarray. So 2 indexes, beginning and the end of the subarray, and some fixed increasing subsequence inside this subarray. And by a score of a segment, I mean length of this fixed increasing subsequence tied to the subarray. Okay, and then we define K1, K2 cover of the whole array as a set of segments, each with score between K1 and K2, such that for any interval, for any subarray, which contains increasing subsequence of length K2, we must have in our collection of segments a segment contained strictly in that subarray. Okay, and we say that such a segment covers that subarray. And it can be seen that it is useful for approximation, right? Then whenever somewhere exists increasing subsequence of length K2, then maybe we don't know this, but we are guaranteed a segment and so an increasing subsequence of length at least K1 inside this subarray. So it can be used for approximation. And as I said, important parameter for us here is depth of the cover, which is defined just as the largest number of pairways intersecting segments. And that's an upper bound for in how many different segments can one element of an array be. So if we keep depth low, then, for example, deleting one element can affect only so many segments. Okay, and it turns out that using specific greedy approach can be used to efficiently compute K1, K2 cover of depth K1 over K2 minus K1. So if we set K2 to be, say, 1 plus epsilon times K1, then this depth is just 1 over epsilon, which is presumably a very small value. Okay, and let me tell you shortly what I mean by greedy approach. So let's say that we are interested in computing free for cover for such an array as presented on this slide. And by a greedy approach, I mean that we scan an array from the left and we find the shortest prefix containing increasing subsequence of length 4. And we promised that we will cover such a subarray. So we need a segment inside this prefix, and we find shortest suffix of this prefix containing increasing subsequence of length 3. And this is our first segment. So this is segment with increasing subsequence of length 3, which covers this prefix. Then we can safely forget about all the elements starting before this suffix. Okay, and we find another. In this new array, we find again the shortest prefix containing increasing subsequence of length 4. And we say that we cover it with its shortest suffix containing increasing subsequence of length 3. And this is our second segment. And we proceed in this manner to the end of the array. and we end up with some collection of segments. Okay, and here depth of our cover is as promised, so it's free because element with value 14 is inside segment 3, segment 4, and segment 5. Okay, so this is a very useful method, but still running this greedy algorithm takes at least linear time. So it's not like we can run this greedy algorithm on the whole array after each update, right? We can use it, but we need some additional properties. And so for that, we will use divide and conquer approach. Okay, so for simplicity, let's say that we are working in decremental version. So there are deletions only, okay? And we need to uplift an array to the set of two-dimensional points in a standard way. So we create a point with x coordinate being its index in the array and y coordinate being a value at this index of an array. Okay, and now finding increasing subsequences translates to finding chains, where chain is just a sequence of points where each next point dominates previous ones. Okay. And additionally, when a point is deleted, then we do not modify x coordinate of the remaining points. We leave them with their initial indexes from the array. Okay. And we would like to work on rectangles spanning over those points. And those would be dyadic rectangles. So a dyadic interval is an interval between two multiplicities of some power of 2, any power of 2. Okay? Two consecutive multiplicities of any power of 2. And a dyadic rectangle is a rectangle with two sides, with both sides being dyadic intervals. So we can use this definition to decompose such a dyadic rectangle. Namely, a dyadic rectangle can be decomposed into either upper and lower dyadic rectangle, right? Or it can be decomposed into left and right dyadic rectangle. And then this forms our decomposition into rectangles. We would like to compute covers starting from the smallest rectangles and going up. Okay, so let us consider some rectangle R in our decomposition. And let's say that we already have covers for its smaller parts. So for left, right, upper, and lower rectangle. And now we want to compute some cover for this rectangle. So first thing we can notice that we can take union of covers from left and right rectangle. Okay, and then by doing that, we are done with any subarray contained strictly in the left or right rectangle. Okay, by definition. And only thing we need to worry about is subarrays which crosses the middle x point. Middle x coordinate of our rectangle, because neither left or right rectangle promised us that it will cover such subarrays. So we need to add some segments to cover such subarrays. And it turns out that it can be done using covers from upper and lower rectangle. By that I mean, let's say that we have a subarray starting at index I and ending at j, and that subarray crosses the middle x coordinate. And there is some chain inside this subarray. So this chain can be cut into two chains. One contained strictly in the upper rectangle, and one chain contained strictly in the lower rectangle. And then, by definition, we are guaranteed to have some good approximation of those two parts in covers of lower and upper rectangles. And if we are able to somehow find those two good approximations and merge them together, then they are good approximation of the initial chain, right? So I can't give you too much details there. And there are several cases on how those parts can be positioned in the rectangle. But basically, the fact is that there are not too many good candidates for such two parts, and we can somehow guess them all and gather all candidates in one place and perform some computation. And the result of this computation is set of segments enriching our cover. Okay, and in general, we need to set a couple of parameters, especially as we are computing approximation in a rectangle using approximation in smaller rectangles. So our approximation factor is only increasing. So in fact, to achieve 1 plus epsilon approximation, we need to use much finer approximation in the decomposition. But that's not a huge issue. And we can get a decremental structure working in polylogarithmic amortized time. And it's not that complicated to firstly extend it to handle also insertions. So both deletions and insertions of points or of elements to the array. Okay. And second thing, we can make it work in worst case polylogarithmic update time, not just amortized. And it's all about the main algorithm. So one particularly nice application of our solution is to Erdos-Chekeress partitioning. So it is well known that permutation of n elements contains either increasing or decreasing subsequence of length at least square root of n. And this in turn means that a permutation on n elements can be partitioned into roughly square root of n monotone subsequences just by extracting this guaranteed longest one repeatedly. Okay, and naive implementation of such a partitioning works in time n to the power of 1/2 times log n. And it was known that we can shave off this 1 log, but not decrease exponent in our polynomial time. But using our approximation of dynamic LIS, we can improve the time complexity to be almost linear. So because we do not really need to find exactly the longest increasing subsequence here, but its approximation would be good enough. Then we can delete the points in a dynamic way and again find increasing subsequence and so on. Okay, so I can end with the main open question there, I think. So that question is, do we need approximation to get down to polylogarithmic time? Okay, so only very recently, Kociumaka and Sedigin designed randomized algorithm for fully dynamic exact LIS, which works in sublinear time. And that time is n to 2/3 times some polylog. Okay. And it's quite complicated already, but it doesn't give much better than linear time. So the question here is, can we hope for some polylogarithmic time solution for fully dynamic exact LIS? And well, we don't know. The only thing we know is that it's not possible for some generalizations of LIS problem. So I mentioned extended LIS queries, in which we can be asked for LIS in any subarray, not just the global LIS in the whole array. Then we have a conditional hardness result saying that we cannot handle such queries dynamically in polylogarithmic time under online matrix vector multiplication conjecture. And we have similar bounds for some other generalizations, but no lower bound better than simply log n is known for the case of dynamic global exact LIS. So there is quite a large gap there. Okay, that's all I wanted to say. Thank you for listening.